Okay, so let's look at how to measure the coefficient of friction. We'll do it with the spring balances we used in class, so you can imagine it won't be super accurate. But what I've got is a bit of a weight, and so and it's an 8 Newton weight, but actually it weighs about 8.1 newtons. This is the spring balances we used, and I've zeroed those for when they're horizontally. And so there's a couple of ways we can measure the coefficient of friction. The first one uses a setup a bit like this. And so we just pull it with a certain force. We pull one of the objects made from one of the materials, give that a pull, sitting on top of the second material. And obviously for equilibrium, so we're going to pull it, this force will increase. We'll always have a balancing friction until it gets to the maximum capacity, which will be Fs, so the maximum friction just before this object slips. And so these two things must be equal. So if we measure P when the object slips, we're essentially measuring Fs. What we'll do is we'll measure it a few times, and we know for this situation that the normal force is just going to be equal to the mass times gravity, which in our case is 8.1 newtons. And so we're using a steel weight, and we're putting it on timber. So there's a timber underneath. And so we'll do that first, and we'll take the measurements. And what we'll do is we'll measure it 5 times. That way we can get a sensible average. So let me do that. So we'll just bring it back. So basically we're just attaching the spring balance like so. Then we're just going to pull that until it slips. And we're going to take a note of the load it slips at. I'm going to try and pull it as straight as I can. So that was 3.8. And I'll do that another 5 times. And then we'll come back again. So we measure that 5 times, got our average, and those then to get the coefficient of static friction. So then we're just going to go the average load at slips, the average maximum frictional force, divided by the normal force. So we're going to get 3.7 divided by 8.1, which is equal to 0.46. Okay, so that's the first way of doing this. The second way, what we can do, let's see if I can manage this. Should be okay. Let me just bring this back so you can see it. So the second way is shown here. So what you do is you put the material underneath, you incline that slope, so you increase the angle of that slope until this block slips, and we'll have a look in a minute about how you figure out the coefficient of static friction from that. But you're changing this angle till it slips, and so we can just use, similar to what we did in class, we can just grab an inclinometer on the phone, make sure we know how we're using it. And so we've got it here. So this is my angle over here. My bench is not quite flat, so like I say, it's a little bit approximate. So then we're just going to increase this. You can't see that. Just a second. I want to catch the weight so it doesn't fly off the end. So we've got 2, 5, 6, 7, 8, 9. So we're just increasing this. Let's move this across so you can see it. So we're up at 12 degrees, 14 degrees. Okay, it's going to go outside your camera in a second. But it'll just keep going until it slips. So that slipped at 22 degrees. So I'm just going to come back and enter that in here. And then I'm going to repeat that another 5 times. So I'll just do that another 5 times. And then I'll come back again. And just being careful here, this here is the angle. This is the percentage inclination at the other side. Okay, so I'll just do that again. Let me just hold it nicely. You've got to kind of hold it perpendicular, otherwise it doesn't measure the right angle. Just see what we get this time. Okay, I'll do that another 3 times. That was 24 degrees that time. So I've measured that angle a total of 5 times now, and then I've found the average. And so what we have to do now is think about, like, how do we figure out this coefficient of static friction from this block on an inclined plane? So we're raising this plane just until it slips. And so we need to figure out how to find that coefficient of static friction. So for these types of problems, what I've done is I've taken that and I'm just drawing a free body diagram of that. And so we've got the weight mg, which is just going to be vertical. And for these problems involving inclined slopes, what we usually do is draw the x and y axes aligned with the slope. And so we've got y perpendicular to the slope and we've got x aligned with the slope. Then what we'll do is we'll take that weight and we'll resolve it into its components in the x and y direction. So it's exactly the same as we've done before, it's just this time our x and y components are inclined. And so remember, when you're drawing the components for forces, you should be drawing them from the same point of application. So these are the components. That should be mg there. And we know this angle is theta. Should be black probably. And we could call this, I don't know, Fy and Fx maybe. So this is the y component of the weight, and this is the x component of the weight. And you could imagine them nose to tail, usual stuff. If you play around with your angles rules, I'm drawing that dash because I've moved it from its point of application. If you play around with your angles rules, you'll find that this here is theta, the same as this angle here. And so we can figure out that, let me just put it back to 100%, zoom back out again and get rid of my ruler. So we would have Fx is going to be equal to mg cos theta, sorry, sine theta. Sine theta is opposite, and Fy is going to be mg cos theta. Now, if we think about equilibrium here, the sum of the x components must be 0, so we must have the friction component in the other direction. So that would be when theta gets to the point where it's just about to slip, that'll be Fs. And so that must be equal and opposite to Fx. And so this must be equal to, and I'll just think about the magnitudes, I'm not going to worry about the directions, which is going to be equal to this Fs. So the magnitude of the x component of the weight is going to be equal to the magnitude of the friction. It's in the opposite direction, but it's just the magnitudes. And similarly, we're going to have a normal force. We'll not worry, in a minute we'll just look at where this would actually be. For now, we'll not worry too much, but let's just say the normal force is around here somewhere. It's going to get a bit messy. I'll just put it there anyway. It's not going to be in the right place, but just there is going to be a normal force. We need to think about moments to figure out where it is, and it's going to be equal and opposite to Fy. And so the magnitude of that normal force is going to be equal to the magnitude of Fy. It's just going to be in the opposite direction. So we'd call this N. And so our coefficient of friction, remember, is just Fs divided by N, which is exactly the same as, let me just put this down, is exactly the same as Fx divided by Fy. Okay, because of these equations that we just written down. And we can see something else. Fx over Fy is just this over this, which is opposite over adjacent. So that is exactly the same as tan theta. And so theta is just equal to the angle of friction. Okay, and so in our case, we've got an average of 24.4. So tan theta, so sigma, this static coefficient of friction is just tan of 24.4, which is equal to, let me just stick it in my calculator, tan of 24.4, 0.45. Now, if we've done this properly, this should be about the same as what we got the other way. And it is. Look at that. So this was calculating it just by looking at the force you pulled along horizontally. We've got 0.46. Using angle and lifting this up until it slips, we're getting a very similar result of 0.45. So pretty happy that we've got the right answer, or we've got a reasonably good estimation of the friction coefficient between that weight and that timber. Okay, so what we'll do next is we'll probably try a few examples, different types of problems you can get with coefficient of friction, and then we'll be done with statics. You can go on, after you do your quiz, you can go on holiday. Okay, back in a bit, bye.